Hey guys, today I'm gonna teach you guys the similarity postulates, and there's actually three similarity postulates. You can look at the title. They're angle, angle, side, and side, side, side. And what's special about the side side is that the angle has to be included in between the two sides. But what's different about these similarity postulates and the congruency postulates, besides the fact that angle works this time, is that we're talking about specifically triangles here. But anyway, is that the sides no longer have to be congruent, but rather they have to be proportional. So let's look at two similar figures that we have here. Now, when we're dealing with similar figures, which means that it's a shape that has more than three sides, not just a triangle in this case, then in order for two figures to be similar, and that is true if and only if their corresponding angles and corresponding sides have to be something. So the corresponding angles have to be congruent, and the corresponding sides don't have to be congruent anymore. That would mean that we're dealing with congruency, but they do have to be proportional by some scale factor. So if I look at these two mountains or some weird pentagon, I believe, yeah, some weird pentagon, it looks like we're going from 6 to 12. So if I look at that, I can actually find a scale factor, couldn't I? So it looks like I'm multiplying by 2. 3 turns into 6, 2 turned into 4, 5 turns into 10, and 10 turns into 20. So just from looking at this, I can tell, well, sure enough, yeah, this looks like it's going to be similar because all the sides are proportional. They have the same scale factor of times 2, and I can do all of that. The other way we could check is by setting up a proportion, right? So I'm going to start with the smallest measurement of 2, and I know the smallest measurement before the scale factor is going to be still the smallest measurement after the scale factor. So 2 is going to correspond with 4. The next smallest of 3 is going to go with the 6. Then after that, 5 is the next smallest. 5 is going to go with the 10, and then we have 10 going with the 20. It looks like I skipped the 6 going to the 12. So I should have done an extra one there, but you get the idea. And then there's two ways to check the extended proportion. We can either cross multiply each one of these or reduce the fractions. And if they all reduce to the exact same fraction, then you're good. This is 1/2, 1/2, 1/2, 1/2, and sure enough, 6 to 12 is 1/2 as well. So you can check the proportions, but honestly, most of the time it's going to be easy enough that you can just visually check to see the scale factor, and then you're good to go. If they're all being multiplied by the same thing, we're fine. So all the corresponding angles, ooh, wait, no, we just said the corresponding sides are proportional, but we do have to check to make sure the corresponding angles are congruent. Especially when we're not dealing with triangles. So for instance, this 6 and this 4 actually could be out there. 4, 4, 6, and 6. What shape is that, by the way? Quadrilateral with 4 sides, 2 consecutive sides are congruent. You said a kite. Yes, good job. So that means those diagonals would be perpendicular. Oh, so fun. But technically, this could be, from the kite, it could be flexed out. Now, if it was flexed out, then all of a sudden, we still have the same 3 going to 6, 2 going to 4, right? So it's still the sides are still proportional, but it's no longer going to be the same shape. So that's why when we're dealing with similar figures like any polygon that's not a triangle, we have to check the angles as well. So it's important the angles are the same because these two technically have proportional sides by a scale factor of 2, but that's clearly not the same shape as what's going on with the mountain. Something that looks like more like a volcano. Kind of cool. But anyway, so yes, we do have to check both conditions. All the corresponding angles must be congruent, and the corresponding sides must be proportional in order for figures to be similar. So here's another example. It's not just enough to look at one of them and not the other. So here we have two squares, and so they are going to be similar to each other if they're squares because all the angles are the same. But if I extend this so that now it's a rectangle, and that's so cool. Oh my gosh. So it's no longer 6. Let's say it's now doubled to 12. Now the sides are no longer proportional, so it's not enough just to check that the corresponding angles are congruent. We have to also check and make sure that the sides are proportional. Now when we have that square, all the 8s go to the same 6s with the same ratio, or the same of 4 to 3, or same scale factor of 4/3. But regardless, now it's going to change. Now we're going to have these values here are going to be 12s, right? So we have the smallest side of 6 going to the smallest side of 8, and then the longest side of 12 is, well, it has to go to those 8s. And so when I cross multiply here, we're not going to get the exact same thing. So when we reduce those fractions, it's not the same thing either. That would be 4/3, and this would be, see, that would be, take out the 4 would be 2/2. Yeah, so 2/3 and 4/3 are not the same thing, clearly. So we have to check, again, not only the angles are congruent, but also the sides are proportional. And what we saw from the last one is it's not enough just to check to see that the sides are proportional. We have to check to make sure the angles are congruent as well. Okay, so that's pretty much your lesson for today. Now let's just get into, that was a review. Now let's get into our 3 congruency postulates. Now, when we're talking specifically about triangles, there are 3 ways we can prove triangles are congruent without having to check all the angles and all the sides being proportional. We can now use angle, side, where the angles included between the 2 sides that are proportional, and side, where all 3 sides are proportional. So let me first show you angle. These are just like our congruency postulates, by the way. And we're going to do a fun activity when we come back in class the next day, where we actually graph these out with compasses and rulers and protractors, and lions and tigers and bears and mice. All right, so if we have angles of 30 and 60, does that mean that these 2 triangles have to be similar to each other? The angle theorem would say yes. It would also tell us that the reason we don't call it angle theorem is because if we know 2 of the angles, we know what the 3rd angle has to be anyway. So the supplement of 30 and 60 is 90, and so this is 90, and this is also a right angle up there. So that's why we can just call it the angle theorem instead of angle theorem. All right, so these 2 are going to be similar to each other. Oops, I should have locked that in place and then moved it. It's okay, I know how to fix it. There we go. All right, so if I slide this over here, love my smartboard, you'll notice that they actually have the same angle matching up here. These 2 angles are exactly the same as well. And what it's going to do is these 2 sides are actually be parallel by that'll be our side splitting theorem, but we'll learn that in about four more lessons. But anyway, you will see that they are going to be proportional. So the growth in the green one is going to be proportional with the growth in the bottom base here, and the growth with the blue one as well. So they are going to be similar to each other. Let me back that back out. Oh my goodness. Oh, okay. So apparently I had to use that. And the other thing is that as I move this in, oh, that's so cool. As long as it's still parallel and it still has the same corresponding angle of 60 and 30, these are all going to be similar. So that's similar. I can blow it up, make it even bigger. It's going to be similar. Oh, that's so aesthetically pleasing. So it doesn't matter. They're just going to be different proportions of all the sides, kind of like we stopped and measured that last time. So much fun. All right, so are these triangles similar? So do they have the same angles? Well, I see 65 is the same as 65, but the other 2 angles are different. But if I solve for the missing supplement, because these all add up to 180, that would leave me with 45, which is the same as that one. Okay, well now that I know that 2 angles are the same, that means their 3rd angle has to be exactly the same as well. So yes, they are similar by the angle similarity theorem, just as an example. All right, so are these 2 triangles similar? Well, I don't know any of the angles, but I know all 3 of the sides. So as long as we have all 3 sides, we can prove their similarity by side. Now, they're not necessarily going to be congruent, right? Now the sides just simply have to be proportional, which means they have to have either the same scale factor, the same ratio, or set up an extended proportion to check. Okay, so lots of different ways you can do it. So my smallest side over here of 6 is going to correspond with the smallest side after the scale factor of 18. By the way, you can probably just tell what the scale factor is. What am I multiplying 6 by to get it to 18? Times 3, right? So what does 9, the middle one, turn into? 9 times 3 would be 27. And the longest one of 12 might be a hypotenuse, so I have to do the Pythagorean theorem converse, but I'm not going to do that. Would be times 3 would be 36 as well. So yes, we can check by scale factor and we're good to go. Other ways we can do it is setting up a proportion. So 6 goes to 18, the middle one of 9, and then the longest of 12, middle one of 27, longest one here. If I reduce all these fractions, or you could cross multiply if you really wanted to. So 6 times 27 and 9 times 18, those are equal to each other. You can cross multiply these as well. And sure enough, those are going to be equal to each other as well. And before you cross multiply, if you're trying to do it in your head, you can just reduce the fractions, and we're going to get 1/3, 1/3, 1/3. Okay, so what's our scale factor? Well, 1/3 is not the scale factor. You got to be careful with the order of scale factor. So it's image divided by pre-image. If we're going from the small one to the big one, left to right, then it's going to be 18 divided by the smallest of 6. So 18 divided by 6, which gives you a scale factor of 3, which makes sense. 1/3 would be going backwards, but we're going left to right, so it's times 3. Our ratio from pre-image to image is 6 to 18. Then we can reduce that as well. So 6 to 18 reduces to 1 to 3, right? Yeah, divided by 6. All right, cool. So if we know all 3 sides, we can prove it. Next one we have is side angle side. So on this one, I know 2 of the sides, but I don't know what x is. We're actually going to solve for x. This is a really good example. And the reason I can use side angle side, because I need to know the angle that's included in between the two sides is congruent. Well, these two are lining up with each other, so this angle that's between the two here has to be the same angle for both of them by the reflexive property, right? Angle A is congruent to angle A. It's the same angle for both of these triangles. So we can set up a proportion and check to make sure the two sides are proportional. So it's not enough just to have the angle, because we don't have another angle. If I knew that angle or that angle or that angle or that angle, then I would know the lines are parallel, side splitting theorem, all that good stuff. But let's do the two sides that are included by that angle. So 4 goes to 8, just as 6 goes to 12. You probably noticed the scale factor. So 4 goes to 8, 6 goes to 12. You could also reduce both of these fractions if you wanted to. You can cross multiply, however you want to do it. 48 is equal to 48, so we're good to go. It also reduces 2/3 is equal to 2/3, or you notice we're multiplying by a scale factor of 2 for the extension, times 2 for the extension. So they're good. Next thing we want to do is solve for x. So if this is going from 4 to 8 is times 2, isn't 3 going to go to times 2 and be 6? Oh, big careful one. So this is probably one of the most missed types of problems from the test, and we're going to go over that misconception right now. So if you notice, the red part is the extension that's longer than the original green small triangle. But if we look at our big triangle, which I'm going to shade as blue, so our big triangle is in blue here, somewhere. There we go. So here's our big triangle in blue. So we're really comparing the green triangle to the blue triangle, before to the after. The red part is just the extension. So for the full length of the blue part, we're going from 4 to 4 plus 8, which is 12, right? We add them together. We're going from 6 to 6 plus 12, which is 18. So that's the dimensions we would have to use in order to solve for the long side here of x. If not, what we were actually doing, and I'll show you just for fun, is that we would actually be finding the extension, which is how much bigger it is from the original 3. And we said, remember, that was multiplying the extension, we'd be multiplying by 2. So that would be an extension of 6 plus the original 3, which we add those together, which actually give us equal to 9, which is fascinating because you could use that method, but it's better not to. So our 4 starts out as 4, and it goes to the long length of the blue one of 12, just as 3, our small one on the green one, goes to the long length, which we called x. Now when I cross multiply, I'm going to get 4x is equal to 48. So then you can divide both sides by 4, and you get x has to be equal to 9. So sure enough, x is equal to 9. Lovely. So fun. And that was proving similarity with side angle side. So side included angle side. And remember, those two sides are proportional, and the angle has to be congruent. All right, so here's an example. Again, we got this included angle here. It's the same angle Q for both of them. So we need to just check now that the sides are proportional. So 2 goes as the extension of 6, just as 3 goes the extension of 9. So let's set it up. 2 goes to 6, just as 3 goes to 9. That's 2/3, that's 2/3. Also, when you cross multiply, we get 18 is equal to 18. So either way you do it, you're totally fine. You can also see a scale factor. We're tripling it. Yeah, multiplying them by 3. So we're actually doing more if we actually want to solve for that one over there. But I won't do that again for you. All right, so that was it. 13 minutes, not too long for the lesson, I don't think. Let's do a bunch of homework together. I spent so much time putting all these homework assignments together, and I made them so beautiful. It's so pretty. And that's why I get no sleep. But it's okay. I enjoyed it. So let's look at number 1. Determine whether triangles are similar. If so, write a similarity statement and name the postulate or theorem you used. If not, explain. So first of all, look at the diagram. What do these markings tell us? Not that. What does that little triangle mean? So this triangle and this triangle over there tells us the lines are parallel. Well, right off the bat, also, what do you know about the angles in the middle? Well, they're vertical to each other. And if we have parallel lines, that means these angles up here are going to be alternate interior to those angles. You also know these angles are the same as that angle, and by the third angles theorem either way. But on triangles, all we need to know is 2 angles. Once we know 2 angles are the same, these 2 triangles have to be similar to each other. And they're similar by angle-angle similarity postulate. Yes, so similar, yes, postulate we're using is angle-angle. The similarity statement, now we want to put these together. So lots of different ways you can do it. We can say that triangle AEB is congruent to, or similar to, and A was corresponding with D, right? So AEB is similar to DEC. I think that's the one I did, yeah. So triangle AEB is similar to triangle DEC. All right, you could do it many ways as long as you have the corresponding parts matching up. You're good to go. All right, number 2, determine if they're similar. So all they give us is an angle and one side that's congruent. Okay, so we don't need sides to be congruent. We need them to be proportional. But if they are congruent, then they are still proportional. They just have a scale factor of 1 or a ratio of 1 to 1, which is not that exciting. But that's okay, still works. So on this one, we still need more information than one angle and one side. We need to know another angle, like the one over here, being the same. Then we could say a similarity. Or we need to know that this side is proportional to that side as well. By the way, we still can't use the donkey postulate, a money sign, for the same reason we couldn't use it for congruency, is that without knowing we had a right triangle, it would be ambiguous, where it could be acute triangle or an obtuse triangle as well. So, but if we knew that there was a right angle, then we could use the donkey postulate. It's not called the hypotenuse leg theorem anymore. At that point, I don't know if it does have a name for similarity. I'll have to think about that one. I'm pretty sure we don't use it. Okay, so are they similar? No. Postulate is not applicable because they're not similar, and we can't give a similarity statement because they're not similar. Number 5. All right, so right off the bat, I know this angle in the middle is going to be reflexive. It's the same angle for both of the triangles. So we would be using side angle side. That would be your postulate. But first, we have to check to make sure it's actually similar. So 2 goes to 6. So 2 goes to 6, just as 3 goes to 7. Cross multiply, I get 14 is equal to 18. That is not true. So those are not equal to each other. So they're not going to be similar because the sides are not proportional. The postulate we used would be non-applicable. Technically, we're using the side angle side postulate. So the inverse of the side angle side postulate. So if the sides are not proportional, then the triangle is not similar. But regardless, we'll just say not applicable because they're not. And then the similarity statement, we can't give that either. So number 7, looks like I'm given all 3 sides, so I just have to check to make sure they are proportional. So the small side of 13, 13, 15. So in order, 13, 13, 15. Small sides in order, 26, 26, and 30. Now you can probably see the scale factor or reduce these, right? We're just multiplying it by 2. These are all reduced to 1/2, or you can cross multiply if you really want to. So they will be similar because the sides are proportional. We use side, 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 and the similarity statement. So on this one, I'm going to start out with my peak here of the isosceles triangle. So MLN is similar to Q. It actually doesn't matter. You could do QOP or QPO because those are base angles are congruent. So there's actually lots of different ways you can do the similarity statement. I think I did MNL and then QOP. But the special one is that M is going to be congruent to Q. So just make sure that your M is corresponding with the Q. The order of the other two actually don't matter because it's isosceles. It's kind of cool. Number 8. So this is like the Boy Scout problem. This is indirect measurement. A lot of funny things I've done in the past on this one. So for instance, I used to draw a shark here with, so we're trying to build a bridge. And we got sharks with freaking laser beams attached to their freaking foreheads. So it's important for us to find the measurement of this, and it's lava. It's a river of lava that's shark infested with lasers on their foreheads. So we have to be really, really careful, and we have to use indirect measurement with us and our buddies to be able to figure out how long the river is to make our bridge. Because if it's too short, it'll fall in the river and it'll get burned up. If we stick around too long, we'll get shark eaten. So good story. All right, so this is actually indirect measurement. You can actually do this with other people, and basically you walk perpendicular to a shore, and then you have you find some object on the other side of the shore, like a bush or a tree or a triangle. It's a tree or a tree right by the shore. And then you line somebody up and you tell them when to stop whenever they're directly in between you and that. Then you measure the distance, that perpendicular distance between you and the shore and the distance along the bank. And then you go across here perpendicular as well, measure that distance. And then you have similar triangles. The reason we know they're similar triangles is because these angles here are vertical, and we made sure that both of these were perpendicular. Just kind of eyeballing it would be good enough. And then that would actually make these lines, of course, parallel, and then alternate interior angles and all that good stuff. So the postulate we're using in this case would be angle, angle, and then we could set up a proportion using the sides. So our distance along the shore of 50, I'm not sure how I set this one up. Yeah, 50 corresponds with the 80, just as the 30 will correspond with the distance here of x. Then there's lots of things you can do. If you notice, these both end in 0, so we could actually reduce that by dividing by 10. So we basically get 5x is equal to 240. Then divide by 5, leaving us with x is equal to 48. So 48 feet is the distance. So when we build our bridge to go across the river of lava that's shark infested with laser beams attached to the freaking foreheads, then we need to make sure it's at least 48 feet. Otherwise, it'll fall into lava. Another cool one, this is another form of indirect measurement. We'll actually go outside and do this at the end of the year, measuring shadows off the top of your heads and some other object to figure out how tall that object is. It's a lot of fun. So Thales was an ancient philosopher familiar with similar triangles, smart guy. One story about him says that he found the height of a pyramid by measuring its shadow and his own shadow at the same time. If Thales was 5 feet tall and at the same time the pyramid cast a 318-foot shadow, that Thales' shadow was 6 feet, then what's the height of the pyramid? So we kind of have this diagram here. I made a newer version. So what's happening is that the rays from the sun, of course, it's just light and it emits in all directions and it lights up our entire solar system. But the rays that are directed, because the sun's so far away, the rays that are directed at the Earth, the only ones that we see are the ones that are actually parallel, that are all traveling in the same direction. So the rays that are going off in the other directions, we don't see those, right? So we can assume all the light, all the rays of the light from the sun, because it's so far away, are all parallel. And so the ray that hits the top of Thales' head and then casts this shadow, so it hits the top of the head, casts a shadow, is going to be parallel to the one that hits the top of the pyramid at the same time. Of course, if you wait 30 minutes, the sun's going to move and then the triangles are no longer similar. But because those lines are parallel, it means that the angle of attack or the angle of elevation is going to be exactly the same. And then we're both standing straight, so it's a perpendicular and perpendicular angle here. So we have two right triangles. By angle, we know they're similar to each other. So we can set up a proportion. So the height of Thales was, or his shadow was 6 feet. That corresponds with the shadow of the pyramid, 318 feet. Thales' height was 5 feet, which corresponds to the height of the pyramid, which we're solving for as x. Okay, so we can actually simplify. We can 6 and 318, that'll actually divide, but you don't have to. We're going to end up putting in the calculator anyway, so I'm just going to cross multiply. So 6 times x is 6x, and then 5 times that is going to be a big number. Just put it in the calculator, divide both sides by 6, and we get x is equal to 265 feet. So the height of the pyramid, which we couldn't measure any other way because you can't, it's not hollow. We can't drop anything or anything like that, is going to be 265 feet, which is kind of cool. All right, another method of indirect measurement. A stick 2 meters long is placed vertically at point A. So point A, 2 meter long stick. And the top of the stick is in line with the top of the tree as seen from point C, which is right here on the ground, which is 3 meters from the stick and 30 meters altogether from the tree. How tall is the tree? Well, first thing is we know we have alternate interior angles, or not alternate interior, sorry. This angle is going to be congruent to itself, and the stick and the tree are both perpendicular. So by angle-angle similarity, I know these triangles are similar, so we can set up a proportion, solve for the height of the tree, which I'm going to call x. So I know 3 corresponds with 30, just as 2 corresponds with x. You actually can reduce this before you multiply, so you can take the 3 out of both of those, so we get 1 and 10. So when I do that, I get x is equal to 20. You also probably can see the scale factor. If I'm going from 3 to 30, multiplying by 10. So what's 2 going to turn into? 20. So how tall is a tree? 20 meters. 15. Explain why the triangles are similar, then find the distance represented by x. All right, we got an angle, got another angle. So we have 2 angles, so our postulate is going to be angle. Now that I know they're similar, I can set up a proportion. So my smallest side of 12 is going to go with the smallest side of 21, just as the hypotenuse of 40 goes to the hypotenuse of 11x plus 4. Now there's some reducing I can do here. I could take out a 4 from both of these, which is going to give me 10 and then 3. And then I can reduce the 3 and the 21, which is going to leave me with 1 and 7. So at the end, when I cross multiply, I get 1 times this, which is nice because then I don't have to distribute. and then 10 times 7, which is 70. Then it's just algebra from there. Subtract 4 from both sides. 11x is equal to 66. Divide by 11. X is equal to 6. Very nice. All right, number 16. This one's not going to be as friendly, if you can see. So on this one, we have parallel lines, which mean, well, this angle is congruent to itself by reflexive property, right? And then the corresponding angle here is going to correspond with this angle right here. They are corresponding angles. Same thing on the other side, right? So they're similar. Our postulate we're using is angle-angle. Pretty much any time you see parallel lines, it's going to be angle-angle by either using corresponding angles with side-splitting theorem or alternate interior angles if they're crossing each other. So let's set up a proportion. So 6 goes to 8, just as x plus 1 goes to 2x minus 4. I can reduce, which will be helpful. I can, of course, reduce across because I could have set it up vertically just easily. 6 goes to 8 as x plus 1 goes to 2x plus 4. Then whenever I do that, I'm going to end up taking out a 2, so this leaves me with 3 and 4. Then I can cross multiply. So 3 times 2x minus 4 is equal to 4 times x plus 1. Now, to get rid of these parentheses, I have to distribute. Oh, isn't this fun? So that's going to be 6x minus 12 and 4x plus 4. Subtracting 4x from both sides, leaving me with 2x minus 12 is equal to 4. Then I add 12 to both sides. Isn't algebra just so much fun? Divide everything by 2, so x is equal to 8. Now, if I printed out the assignment, I think I made a mistake last year whenever I was checking this. So I put the answer as 19, but it's actually 8 on the answer bank. Or on the answer bank it was 19, but the real answer is 8. I think I updated it if you're doing it online and on the PDF. All right, number 18. Oops, forgot to hide that. Spoilers. Again, we have alternate interior angles and vertical angles. So these two sides here are going to be the ones that are in between the two congruent angles. So it's 12 is going to go with a 6. See, they're in the same location, included in between our two congruent angles. So 6 goes to 12, just as 7x goes to 42. No problem. We can reduce first. There's a lot of things we can do to reduce here. 6 and 12 is going to be 2 and 1, and then 2 and 42 is going to be 1 and 21. So essentially, we get 21 is equal to 7x, which divided by 7 leaves us with x is equal to 3. How nice. The postulate we used, by the way, was angle-angle again. Anytime you see parallel lines, it's going to be angle-angle. And x was equal to 3. Good stuff. 23. All right, so these are our ratio and proportion problems. So similar to the assignment 8-1 with all of you guys left. Hopefully now that we've settled that and you've kind of slept on it, maybe now it'll be easier for us to put these together. So let's see. The ratio of two complementary angles is 7 to 11. Complementary means they add up to 90. So these two angles, 7x and 11x, have to add up to 90. So add them together is going to be 18x is 90. Divide by 18, and we get x has to be equal to 5. That's our scale factor from the model. That's what we reduce from our unreduced ratio. So to go back to find out the smaller angle, we just multiply 7 times that 5, which is going to be equal to 35. So our unreduced ratio would have been 35 to 11 times 5, which is 55. So the unreduced ratio was 35 to 55. Then we reduced it by dividing it by our scale factor of 5 to get a reduced ratio of 7 to 11. Okay, hopefully that makes sense. Another one, two non-right angles of a right triangle. If you draw a picture, it'll make more sense. Well, if this is 90 degrees, the two non-right angles have to be complementary because altogether they add up to 180, right? So again, 1x plus 5x, because that's a ratio of 1 to 5, is going to add up to 90 again. So 6x is 90, so therefore divide by 6, and x is going to be equal to 15. So what are the measures? Just multiply it back. So that's going to be a ratio of 15 to 75. And again, that would be our unreduced ratio. We divided them by 15, which gave us a reduced ratio of 1 to 5. All right, an animal shelter has 104 cats. Kind of like the balloon example, right? Ratio of cats to dogs is 5 to 3. So how many cats? So 5 plus 3, which is like in our small model, which is going to add up to 8x, where x is our scale factor, has to add up to 104. Divided by 8, which leaves us with x is equal to 13. That's our scale factor. So we'll back, multiply our scale model of the cats of 5 times 13, and that'll give you 65. And then multiply the 3 dogs for a small model times our scale factor 13, and that'll give you 39. All right, so that's all I've got for you today. If you have any questions, let me know. When we come back, we're going to do a super fun assignment with compasses pretty much the entire time. So I will see you later, and looking forward to seeing you in class tomorrow. And we're doing our retakes together as well. So I'm still coming in under 30 minutes.